Good day, my name is AndrewSeenath, and my final year project is the thermodynamic design and optimization of a 10 megawatt geothermal power plant. This project was chosen since geothermal energy is relevant to the Caribbean, since several of its islands possess the volcanic activity below the Earth's surface to harness this geothermal energy. It was also chosen because of the global push to switch to renewable energy production. There are three main types of geothermal power plants: vapor-dominated dry steam, liquid-dominated flash steam, and binary systems. The type of system used is dictated by the enthalpy of the fluid below the Earth's surface. If the fluid is at high enthalpy and contains only steam and no water, dry steam systems can be used. If the fluid contains only water and no steam but has a high enthalpy, flash steam systems are used. If the fluid contains water and has a low enthalpy, binary systems are usually used in this case. The problem statement for this project is what configuration of the turbine, condensers, and cooling towers would be most suitable for a 10 megawatt geothermal power plant in the Caribbean. The aim is to design and optimize a 10 megawatt geothermal power plant. The scope for this project is that all calculations were done with respect to the Caribbean. All calculations were done to achieve a 10 megawatt output, and the types of geothermal power plants analyzed were dry steam, flash steam, and binary power plants. The overall objective is to determine the optimal operations and design parameters for each cycle, as well as to design and optimize the turbine, condensers, and cooling towers. The objectives for the turbine are to find the ideal blade height, exit velocity, and number of rows for each type of geothermal power plant. The objectives for the condenser are to determine whether a direct contact condenser or surface condenser should be used, to find the mass flow rate of cooling water required for each type, and when necessary determine the ideal number of tubes for the surface condenser used. The objectives for the cooling tower is to design a cooling tower that can cool the brine and condensate to below 40 degrees Celsius with minimal or zero power consumption. It was necessary to determine the potential for geothermal energy in the Caribbean. The image on the left is from the West Indian Journal of Engineering. It was published in 2020, and it shows the geothermal potential for the eastern Caribbean islands. The image on the right was published by the World Bank in 2013, and it also shows the estimated geothermal potential for the eastern Caribbean islands. Some common practices which were found are as follows. According to a paper called Geothermal Power Plant Condensers in the World, which was published in 2015, direct contact condensers are commonly used in dry steam and flash steam power plants, while surface condensers are often used in binary power plants. It was also found that cooling towers are not always used. According to a paper published in 2010, which analyzed the geothermal power plant in Guadeloupe, a cooling tower was not used in the Guadeloupe power plant. Instead, a cooling tank was used to cool the water to a temperature which was below 40 degrees Celsius, and then it was injected into the sea. The paper, Injection of Waste Geothermal Fluids, explains the purpose of re-injecting waste fluids into the reservoir. According to the paper, it is done to maintain the well pressure. It is also more environmentally desirable. In some cases, this may not be necessary, however, since the well may have a natural regeneration supply. Finally, the environmental impact of geothermal power plants was considered. The bar graph on the left was published in 2020. The columns GT flash and GT binary represent geothermal power plants. It can be observed that it produces much less carbon dioxide than the alternatives. table on the right shows some of the negative impacts geothermal power plants can have on a given area. The stars on the table indicate the level of effect it has. The following are a list of equations which calculate the input energy, plant efficiency, and hourly rate of energy produced. The blade power output, energy per second, diagram of blade efficiency, stage efficiency, and overall efficiency was calculated for the turbine using the following equations. The inlet angle 2 of the turbine was varied to find the optimal angle. Then the optimal parameters was used to calculate the blade height. For the condenser, the mass flow rate of cooling water to cool the working fluid was calculated. This was calculated for multiple variations of the condenser. Firstly, the size of the water supply for cooling was varied. Both of these designs required a cooling tower. Calculations were also done for a design without a cooling tower. This was calculated for multiple variations of the condenser. Firstly, the size of the water supply for cooling was varied. Both of these designs required a cooling tower. Calculations were also done for a design without a cooling tower. For the surface condenser, the mass flow rate of cooling water was calculated, as well as the number of tubes required. The size of the water supply was also varied. One of the design options also contains a cooling tower. For the cooling tower, the mass flow rate of the moist air at entry was varied to arrive at an amount which can cool the working fluid and condensate to a temperature below 40 degrees Celsius. The following is the data collected for the dry steam turbine. The graph on the left shows the results of angle variation on the turbine. It shows the effect it has on the stage efficiency. The table on the right shows the effect variation of the number of rows of the turbine has on its energy supplied, blade efficiency, stage efficiency, and overall efficiency. The following are data collected for the dry steam direct contact condenser. Options 2 and 3 require a large water supply for cooling. The tables below shows the result temperature variation will have on the mass flow rate for options 2 and 3 respectively. The following is the data collected for dry steam cooling towers. Design options 1 and 2 required cooling towers. The table below shows the average, best case, and worst case scenarios for exit temperatures of the cooling towers. The variations are caused by the relative humidity in the air and air temperature. These tables are for option 1 and 2 respectively. Similar results were acquired for the flash steam system. The following is the results for the flash steam turbine. These are results for the flash steam direct contact condenser. And these are the results for the flash steam cooling tower. The binary system turbine was similar to the results previously found. The tables below shows the results variation of outer diameter and material has on the number of tubes of a binary system's surface condenser. And this table shows the difference in results for a double pass surface condenser and a single pass surface condenser with respect to the number of tubes required. Similar cooling tower results were found for the binary system. Option 1 of the binary system does not require a cooling tower. The following is ideal specifications for the surface condenser which is used for this design. Based on the results acquired from calculations, The following is the specifications for the ideal turbine required. For dry steam option 1, approximately 2000 kilograms per second of water is required to enter the condenser, and 745 kilograms per second of moist air will be required to enter the cooling tower, and approximately 18 kilograms of makeup water will be required by the cooling tower per second. For option 2, approximately 1818 kilograms per second of cooling water will be required to enter the condenser. 318 kilograms per second of moist air will be required to enter the cooling tower, and approximately 8 kilograms per second of makeup water will be required. The large difference in the amount of cooling water required between option 1 and 2 is because option 2 uses a large water supply, which commonly operates at a lower temperature than which the cooling tower can provide. Option 3 does not require a cooling tower, and 911 kilograms per second of cooling water is required for this option. The following is the ideal specifications for the flash steam turbine. Option 1 of the flash steam system requires approximately 200 kilograms per second of cooling water, approximately 750 kilograms of moist air entering the cooling tower, and approximately 14 kilograms per second will be required to the cooling tower for makeup water. For option 2, approximately 1819 kilograms of cooling water is required by the condenser per second. 311 kilograms per second of moist air will be required to enter the cooling tower, and approximately 14 kilograms per second of makeup water is required by the cooling tower. For option 3, no cooling tower is required, and approximately 933 kilograms per second of cooling water is required by the condenser. The following is the ideal specifications for the binary systems turbine. Option 1 of the binary system does not require a cooling tower. The following is ideal specifications for the surface condenser which is used for this design. Design option 2 does use a cooling tower, and the following is the design specifications for the surface condenser used for this design. Analysis was done to see which option of which geothermal power plant was the most suitable. For the field of input energy, the higher values are seen as more favorable, and for the remaining fields, the lower values are seen as more favorable. Whichever option was best for a particular category received an A. The second best received a B, and third best received a C. The options that didn't place first, second, or third was given a U. The most suitable design was decided by which option had the most A's. If there was a tie, the tie was broken by the option with the most B's, and if there was still a tie, the tie was broken with the option with the most C's. The reason why having a lower mass flow rate is seen as more favorable is because having a lower mass flow rate means pumps with lower power can be used. Based on the rating system used, binary system 1 and 2 was tied for most suitable. The turbine inlet pressure was selected to be 6 bars. This was kept for all calculations. 6 bars was selected because this is the inlet pressure of the turbine in the geothermal power plant in Guadeloupe. Similarly, the operating pressure of the condenser was selected to match the geothermal power plant in Guadeloupe, which is 75 millibar. For the surface condenser, the operating pressure was chosen to be 90 millibar. This value was chosen because it was considered to be a reasonable operating pressure for a surface condenser in the Caribbean. A natural induced draft cooling tower was selected to be used in the project. This is because it uses less power than a mechanical draft fan cooling tower. Injection of brine and condensate into the well is done in all configurations for this project. Injection allows for a longer lifespan of the reservoir by maintaining the pressure of the wells. This is also common practice in geothermal power plants. The table below shows a comparison of all the geothermal power plants and their different variations. While a comparison can be done between the different types of geothermal power plants to determine which one is most efficient, this may not be practical, since the type of geothermal power plant chosen is highly dependent on the enthalpy of the fluid within the reservoir beneath the Earth's surface. And the various options are dependent on whether or not there is a large reservoir of water nearby to cool the fluid entering the condenser. However, from the information in this table, as well as the table in the analysis section, it can be seen that the binary system outperforms the rest. This section will examine what factors causes a certain geothermal power plant to operate at a high efficiency, energy output, or reduced mass flow rate of cooling water. The first factor which causes an increased efficiency is the enthalpy of the fluid in the well. The greater the enthalpy the fluid of the well can be extracted at, the higher the input energy. Having a large cooling supply of water can also help efficiency, since this large supply of water can reduce the mass flow rate of cooling water required. This is accomplished since a large reservoir of water usually contains water at a lower temperature than which a cooling tower can provide to the condenser. It can also provide the benefit of not needing a cooling tower, such as the geothermal power plant in Guadeloupe. Having a lower operating pressure of the condenser can also increase efficiency, since this pressure is the exit pressure of the turbine. This is why in option 3 of the dry steam plant and flash steam plant, the operating pressure of the condenser was lowered. It was done to show how it would affect the efficiency of the plant. By doing so, it eliminates the need for a cooling tower, which was previously needed to lower the temperature of the waste fluid to below 40 degrees Celsius. The ideal operating conditions for the components of a 10 megawatt geothermal power plant in the Caribbean was found. Design and optimization was done for the turbine, condenser, and cooling tower. And natural conditions of the Caribbean were taken into consideration, as well as the availability of cooling water. Future work can focus on the optimization of other components such as pumps, steam air ejectors, heat exchangers, other types of cooling towers, and condensers. Further research can be done on the double flash steam power plant and regeneration in the binary cycle, as well as expansion of the scope to Latin America. Thank you for watching.